Hello. So if you were here at all last week, maybe you're tired of the Ginsburg-Sands theorem by now. I don't know.
Never tired.
But I thought it would be fun, since I don't normally get to go into very much detail on some of my proofs, since Demir already sort of introduced a lot of this, that it would be fun to sort of show you some more details. So I'm going to go over some of the background will overlap, and so I might go through it a little bit quickly, but I'll review that for, if you forgot or if you weren't here. So first, this paper that kind of inspired Ginsburg, Sands, and reverse math was this one from the 70s from Ginsburg and Sands. And the main theorem in it is that every infinite topological space has a subspace homeomorphic to one of the following topologies on omega. So either indiscrete, initial segment, final segment, discrete, or cofinite. And I'll just give you an outline of how this was originally proved so that you can kind of get an idea of the setup and sort of understand why we chose certain weakened versions, where those are coming from. Right, so we start off, we fix an infinite topological space X, and we also sort of set up this idea of this closure relation that whenever I put an element X in there, it gives me the closure of the singleton set X. And from here, what we do is we can define an equivalence relation on X so that X and Y are equivalent if their closures are equal. So from here, if there is an infinite equivalence class, what does that mean? It means everything in that set has the same closure, which means it's going to be an indiscrete space. So if there isn't an infinite equivalence class, then that means it's an infinite set. There needs to be infinitely many of them, and they're all finite. So I can pick a representative from each of those and sort of thin it down, and then I don't have any equivalence classes with more than one element in it. And so that's going to mean it's a T0 space. So remember, T0 means that anytime I pick a pair of elements, for one of those elements, I can find an open set that contains that one, but not the other one. It's not always the case that I can do that to both of them, right? But it's at least one. So that's what distinguishes it from T1. Okay, so notice that the rest of the subspaces that I have to choose from are all T0, so good. Now I actually can form a partial order by saying that X is X less than Y if and only if X is in the closure of Y. So if I have a partial order, I can use something called the chain-anti-chain principle, which says that for every infinite partial order, there is either an infinite chain or an infinite anti-chain. So I do that first. If there's an infinite chain, now I can use something called ADS, so ascending, descending sequence principle, and that tells me that there's either an infinite ascending sequence, and this corresponds to the final segment topology, or there's an infinite descending sequence, and hopefully you can tell sort of the dual of a final segment, it should be the initial segment, right? The other case is if there's an anti-chain, that's going to form a T1 space, right? Because nothing is in the closure of anything else, so I can separate everything. Okay, remember there are two T1 spaces. Those are the last two cases. There's either cofinite or there's discrete. So let's say that it doesn't have a cofinite subspace, or it doesn't have an infinite cofinite subspace. And then we can sort of use induction on this fact to form a discrete subspace, right? We can just keep finding a point and taking complements, right? The complements of the open sets are always going to be infinite, right? So we can always figure this out by induction. All right, so then we have proved it. It has to fall into one of those categories. Okay, so first, I'm going to sort of formalize this for reverse math. So notice, it seems like it could be something, a good candidate for reverse math, but we kind of have to reformulate things. We need it to be countable, right? So we're going to use this idea of second countable spaces, which was formalized for second order arithmetic by Dirac. And so this is basically just, you have a triple, you have your set, your collection of open sets and a function. And the function is sort of witnessing that this is a basis, right? So if I have an x and it's in the intersection of ui and uj, then the k function, when I plug in the x, the I, and the j, is going to be a set also containing x that is in that intersection. I'm not going to really refer to this very much, but I just want to show that to you so that you're convinced that I can talk about this in reverse math. Okay, so now we can talk about Ginsburg-Sands as in reverse math. And so we would say it's basically, it should look familiar to you, but now I'm saying that every infinite CSC space has an infinite subspace, which is indiscrete, has the initial segment topology, has the final segment topology, is discrete, or has the cofinite topology. And in a paper that I co-wrote with Andrew Delapo, Dimir Javarov, Reed Solomon, and Java Viliano, we showed that GS is equivalent to ACA naught over RCA naught. But also, another interesting part is that it's also equivalent to the statement that for every CSC space, the closure relation exists. So we kind of get this idea that maybe some of the complexity of this is coming from the fact that in the proof we had to sort of come up with this closure relation. And so it still feels a little unsatisfying to just leave it at this, right? Because there's other elements of the proof. It doesn't feel like sort of the main idea is this closure relation, right? There's some other things that are going on. There's like CIC and ADS, and then there's this induction. So what I'm going to look at in particular, and in the paper we established several weakened versions, but one of them that I found very interesting was this sort of WGSCL, which states that every CSC space for which the closure relation exists has an infinite subspace, which is everything we had before, except for now instead of saying discrete or cofinite at the end, I'm just combining those into T1. So what we have here that is weakened is the fact that we're just assuming that the closure relation is given to us, right? So we don't have to worry about constructing that or anything. And then also, we don't have to worry about the induction step at the end. We can just sort of end right there, right? And so what's interesting about this one is that if you read in the original paper, one of the claims was that this theorem is an interesting consequence of Ramsey's theorem for pairs, right? And if you think about some of the consequences we know for Ramsey's theorem for pairs, you'll recognize CAC and ADS are both strict consequences of RT22 over RCA naught. And so that was sort of a big idea in the paper as they were talking about CAC and ADS. But before we showed, if you're looking at it from reverse math, it's actually equivalent to ACA naught, which is not a consequence of Ramsey's theorem for pairs. But this sort of WGSCL, I feel like, is what Ginsburg and Sands had in mind when they were saying that, right? Like, you're not going to be, I think most mathematicians that aren't logicians would probably not think about this closure relation and whether it exists and how complicated that makes it, right? So they probably weren't thinking about that particular part. And also, induction at the end, a lot of people would just say, oh, induction is something you can do in math, right? So really the core of this argument is the use of CAC and ADS. And so one thing that we showed about WGSCL is it is in fact equivalent over RCA naught to CAC, which is a consequence of Ramsey's theorem. So let's think about, I'm not going to, show this proof because you can kind of see it in the original proof. Right, you just sort of assume you already have the closure relation, you don't have to figure out that, and then you just skip the part at the end with the separating the T1 cases. So notice that we use both CAC and ADS in this original proof. So even if I weaken it to this, right? First, I'll still make the equivalence class, right? But now I don't really, it's not gonna be as complex because I already just have this closure relation given to me. And then I just have, I have to use CAC, and that separates the T1 from the T0 cases. And then I use ADS, that is going to separate final segment from initial segment, right? So what I'm doing is I'm using both CAC and ADS to show this, right? Which is fine because ADS is known to be a consequence of CAC over RCA. So I can use CAC and then I can use ADS. That's not going to change this equivalence over RCA naught. But it still feels like incomplete a bit. It still feels like it doesn't tell me the whole story to just say it's equivalent to CAC because I know that there's this use of ADS. And so what's interesting to look at, to just sort of go into more detail on this, is to think about it from the framework of Weierach reducibility. So let's talk about WGSCL and all the others, so CAC and ADS, as instant solution problems. I'm going to define instant solution problems. There's other ways to define this, but just think of it as a partial function from some sets of objects and the power set of set B. You could think of it as a total function if you sort of restrict A to precisely what you want the instances to be. Otherwise, it's going to be partial if you don't restrict it as much. But the elements of the domain of P are called the P instances, and the elements of P of X, where X is some P instance, are called P solutions to X. And so sort of the way that you should be thinking about this, why these are called problems, is that, so any theorem of the form for all X such that X has some kind of property, there exists some Y such that X with Y has some sort of property. Right, so a lot of theorems in math are sort of formulated this way. Right? You have some sort of object, and if it has some certain properties, you can find some other object from there that has some other properties, right? So think of Ramsey's theorem for pairs, think of things like the intermediate value theorem, anything where you're sort of showing the existence of something for all. Okay, so notice that, okay, well, first I'll talk about how we can compare these problems to each other. So there's a notion called computable reducibility. And here, let me draw some of the standard pictures on the board. So let's say we have a problem P and a problem Q, and I have some instance X of P. I would say that it's computably reducible, or P is computably reducible to Q, if I can somehow compute this, using this X, I can somehow compute an X hat, and then whatever I can, whatever is a solution to X hat, so let's say Y hat, I can compute possibly with the original instance X. So I would say X join Y hat. I can compute a solution to the original instance X. So I'm going to say Y. So this is computable reducibility. And the idea of this is that, right, I can kind of, if I know how to solve a problem Q, then I can also solve a problem Y computably from that. I can sort of code it in there. So notice that this is not uniform though, right? Like I might have different cases, like if the instance it looks like this, then I can compute it in this way, and if the instance looks like this, I can compute it in that way. So if I want to use a uniform version, that's called Weierach reducibility. And so you have these specific functionals, so let's call them phi and phi. I'm just going to overlay it like this. I can still refer back to the original instance, right? And so very similar, it's just uniform. I can pick out these exact functionals to use. Right? There's also strong versions of each of these. So notice in each of these, I was referring back to the original solution. I can also just get rid of that requirement. So I can just kind of code everything into here and then not have to worry about this anymore. Right? So that would be a strong version. Okay. So you can kind of think about it like this. This is how they're all related to each other, right? So we have this strong Weierach is the strongest, right? So it's like uniform and you don't have to refer back, right? Then you can either make it so that you can refer back to the original instance, or you can make it so that it's not uniform, that weakens it. And then from there, you can make it not uniform and make it so that you can refer back to the original instance. So it's good to keep this in mind when you're proving stuff, because if I can prove that something's Weierach reducible to something else, then I get that it's computably reducible for free. I don't need to also prove that. And then the contrapositive is also true, right? If I can prove that it's not computably reducible, then it shouldn't be Weierach reducible anyway. Also. Okay. So the theorem that I have is that WGSCL is not computably reducible to CAC. And so that idea is coming from the fact that we had to use CAC and ADS. And so what you would really want is a composition of those two instead of just CAC. And the reason I can do this is you can think of both of these as instance solution problems, right? So WGSCL, you're going to be given a CSC space, and then also the closure relation that you can use, right? CAC, you're going to be given partial order, and then, you know, from there you have your solutions. Okay, so what makes something like this a bit easier is if I can find something that's more closely related to CAC that I can say WGSCL is equivalent to, right? Because I have this topology problem over here, and I have combinatorial problem over here. So if I could find some other combinatorial problem that sort of resembles CAC in a way, then I can just sort of get rid of the need for topology. Okay, so here's a couple of new combinatorial problems. So the first one is ADAC, and you can sort of think of ADAC as combining CAC and ADS, right? So you start off with a partial order, and instead of just getting chain or anti-chain, it's anti-chain, ascending sequence, or descending sequence. QADAC, I'm going to do that on quasi-orders. So remember, quasi-order is similar to a partial order, but there is no requirement of anti-symmetry. So there could be equivalence classes. So So the solutions are going to be infinite sets that are either anti-chain, equivalence class, ascending sequence, or descending sequence. So notice it just has one extra solution from ADAC. And we also have these implications over RCA naught. Okay, so going this direction, right, this is a subproblem of that because every partial order is a quasi-order. This is sort of a simpler version of that because I don't need to distinguish between the ascending or the descending sequences. I can just say that they're a chain. This one is already known. Also, these reverse. So I believe in this direction, right? We can get this from chain and ADS, or CAC and ADS, right? And since CAC implies ADS, we can use both of those to get back there. And then QADAC, we also need B sigma 2 in order to go that direction because we need to have that case where we have this, we check if there's an infinite equivalence class, right? But that's fine because ADS implies B sigma 2. So I can still use anything along there. Okay, so these problems that I came up with over RCA naught are not that interesting, right? Because they're just equivalent to CAC. But in terms of problem reducibility, they are more interesting because they are distinguished from each other in that sense. Okay, so let's prove some stuff about these. First of all, the fact that QADAC is what we want to sort of replace WGSCL. So, right, we can kind of just think about the solutions and then how they correspond. So in an equivalence class, right, we just think back to the original GS proof. The equivalence class is going to correspond to the indiscrete topology. Anti-chain would be T1 topology. Descending sequence is initial segment, and ascending sequence is final segment topology. Right, so that's actually strongly Weierach equivalent to each other because notice that either direction I go, I don't actually need to refer back to the instance originally because it's very, it's perfectly coded in each of those. So I don't need to do anything extra to find that. It should just be the same set. Okay, so another thing is that QADAC is computable from ADAC. And sort of how to do this, right? It's basically what we've seen before. You check if there's an infinite equivalence class. But this time, right, I can't have an equivalence class in ADAC, in an ADAC instance, right? Because there is no, it has to be anti-symmetric. So I can't have that. So instead, what I do is I take this infinite equivalence class and I make it the complete opposite. I just make sure when I transfer it over, nothing is related. Everything is incomparable, right? And then what I have is just this giant anti-chain. Any subset of that is also going to be an anti-chain. So that's going to be a solution in QADAC because right, that's going to correspond to the equivalence class from before. Otherwise, what we can do, sort of like before in the GS proof, is we can thin this so that there are no non-trivial equivalence classes. So right, so we don't want anything equivalent to anything else that it's not equal to, right? So we just thin it down, and now this is a partial order. Notice that that's computable to do that. It's a partial order, so it's an ADAC instance, and then whatever solution to that is also going to be a solution to QADAC. Okay, so that's not too difficult, but what I want to point out is that this does not appear to be, or as is, this is not uniform, right? I had to separate it into these two cases. And it's possible that I'm just not being clever enough, but it seems like it's more than that. So the conjecture is that QADAC is not Weierach reducible to ADAC. right? It feels like, there's this extra solution that can kind of be utilized, it can kind of be exploited to make it non-uniform. And so that there's a good reason to believe that that's true. So though I haven't showed this part yet, I have proven sort of a baby version that has fewer solutions to it, so it was a little easier to do. And so I'm going to define something called QADS. And this is a lot like ADS, but I'm going to call, I don't know if this is a real term, but a quasi-linear order, which is basically a linear order except for that there's no anti-symmetry requirement. So again, I can have equivalence classes. And the theorem is that QADS is not Weierach reducible to ADS. And so hopefully you can kind of see I'm making this connection that these are both kind of the quasi versions, so the non-antisymmetric versions of these. Each of them have this extra solution I can have, which is an infinite equivalence class that this other one cannot have. So they're kind of similar, but this one again also has anti-chain possibility. All right, so this is the proof that I'm going to go a little more in detail on since I have a bit more time. And so the way that this proof is going to be done, I'm going to start out making, a very typical way of showing non-Weierach reduction is to assume that it's true witnessed by these functionals, so phi and psi, and then show that that somehow doesn't work. So what I'm going to do is I'm going to start building a quasi-linear order. So that's on the QADS or the QADS side. I'm going to call it Q prime. So I'm not using Turing jumps at all in here. So anytime you see a prime, that's just how I labeled the thing. So I'm going to start off with this sort of preliminary order, and then from there I'm going to sort of tweak it a bit, and then eventually I'll get what I want that sort of contradicts this Weierach reduction. So I'm going to build this Q prime in stages. So it's going to be QS at each stage. And so at each stage, so let's just say stage 0, what I have is this one infinite equivalence class, and that's all I have, right? I don't know how to draw that, just all of this stuff. Everything is just equivalent. And then at each stage, what I'll have is S+1 equivalence classes, and exactly one of them is going to be infinite, right? So I'll have something like, I don't know, these finite equivalence classes, and then at some point I'll have this infinite, let's say this is the infinite equivalence class, and I might have some stuff down here too. And what I'm trying to do is, meanwhile, I'm trying to satisfy these requirements, the RE, that phi E is not a Q prime solution. And it'll be clear why I'm doing this later. So the way we try to figure out where this infinite equivalence class is going to go is going to depend on sort of how we've, what we've done to satisfy these requirements, right? Like we're trying to make sure that it's not going to be, that phi E is not computing, right, like, phi E is not computing a solution, so we might require that certain things are large or small, right? And so this equivalence class is going to have to fit in there somewhere. So let's say we're at stage S. What we do is we are going to construct, right? So we keep just making sure we're kind of checking everything's going to be in this, cofinitely many things are going to be in this equivalence class. And then what we do is we keep going until we find a finite set, right? And we're going to like sort of keep increasing these finite sets so that they're increasing. So we just kind of make that distinction so that they're disjoint. We find a finite set, so this is going to be on the ADS side, that is ascending or descending sequence in this phi of that S stage, right? Such that when I map it back to the QADS side, it's going to converge on two elements in this infinite equivalence class, right? Because that's the only part so far that could be a solution, right? It can't be an ascending or descending sequence yet because I don't have enough stuff. And it also can't be in any of these equivalence classes because they're finite. So this is the only option that I have, right? So as soon as I see that, I don't want to have this infinite equivalence class anymore. So I'm going to start. I'm going to sort of start over from anything bigger than those and make a new infinite equivalence class and just keep iterating that process, right? And I know that I can keep doing that because if I can't, right, then I've already sort of shown, like I'm already done at that point. So I'm going to assume that I can keep going. All right, so Q prime is going to be the limit of this. And so what happens is now, instead of having one infinite equivalence class, I'm just going to have this sort of chain of finite equivalence classes, and there's infinitely many of them. It just keeps going. And so notice that any solution in here would have to be an ascending chain or a descending chain. I've made it so that it's impossible to do an infinite equivalence class anymore. So let's assume without loss of generality, right? I had all these finite sets, right? And they're each sort of a fragment of either an ascending sequence or a descending sequence, right? So we can find infinitely many of one. So let's just say it's ascending, right? It could also be descending. So I have these, I've thinned it so that they are all ascending sequences in that ADS side. So the claim is that the maximum, so the phi of Q prime maximum of each of these is going to be phi of Q prime large. So that was sort of the point of these RE requirements, or one of the points of these RE requirements, is to make sure that that happens. So if that's not true, then there should be a computable linear order in phi of Q prime. And the reason for that is I can choose whichever one is not large and like look at the set of everything that's greater than that. And that's going to be my new linear order that's computable, right? And so that can't contain an infinite ascending sequence by construction, right? Because then I could tack that onto the F that gave me that. And then I've already diagonalized against that. So I can't, that can't happen because then when I transfer and map that back to the other side, then I shouldn't get a solution. So I would already be done. So what has to happen is, so anytime I have a computable linear order, it's a well-known fact that if there aren't any infinite ascending sequences, then there has to be an infinite computable descending sequence, right? And this contradicts our RE requirements. We made sure that there were no computable solutions, right? So then if I map backwards, that should also be computable. I made sure that that can't happen. Okay, so now that we know that they're each of those maxima are large, what I can do is I can kind of thin this set even further to make sure that the maxima are descending in the phi of Q prime. And then once I get that, what I have is this set D that's just made out of all of these maxima. So that's going to be a descending sequence in phi of Q prime. Oh, sorry, I didn't mention that. So large you can think of as it's greater than cofinitely many. So there's only like a finite amount of elements that are greater than it. Yes, thank you. Okay. Right, and then, if you were doing descending sequences, we would talk about small, and then that would be cofinitely many or greater. Okay. So, psi of q prime join d, right, is going to map to a solution of q prime, right, because d is a solution on the other side, right? So it will just, by our assumption, this should map to a solution. And like I already said, it has to either be an ascending chain or a descending chain, sequence, right? It can't be an infinite equivalence class because there aren't any. Okay, so what does that mean? It must mean that in our D, so in our solution on that side, there has to be some elements that both converge on this, so psi of q prime join D, and equal 1, right? So they are going to map to solution, and they have to not be in the same equivalence class, right? Because they are, because that can't be a solution. So this is going to immediately tell us if it's an ascending chain or descending chain. Ascending chain, we would say like it sort of matches the natural order, and descending is the reverse of that. So we can tell if it's an equivalence class, or we can tell if it's an ascending chain or a descending one. So let's just say U is sufficiently large to sort of capture all of this information, right? So enough of D and enough of the Q prime order that both of these converge, and so we have all of that information. So just picture U being large enough, right? It's still finite. We can still get all of this information in a finite amount of use, right? But I just want it to be large enough. So I'm going to define this new quasi-linear order Q, and it's the same as Q prime on anything that's less than or equal to U. But, right, so let's say we had some sort of U somewhere, and then we get rid of the rest. And then it's just like a little part of that. Okay, so there exists some computable linear order with no computable solutions, so this is something that's known. And we can just sort of attach that, so the rest of the quasi-linear order is going to be that, and I decide whether it goes, it's greater than everything else or if it's less than everything else based on if the solution looked like it should be an ascending sequence or a descending one. So if it starts to look like an ascending sequence, then I put it below everything because then it can't be. And then if it starts to look like a descending sequence, I put it above everything. The same sort of idea there. So at that point, we can't extend to a solution that maps to a solution of Q. Sort of that's the idea that I have in mind. All right, so now we're looking at this set D0, which I'm defining D up to U. And it turns out that each element of that is also phi of Q large. Of course, I can't just say because that was the case in D because the order has changed. So I can't just use that same exact, I can't just restrict it and say it's fine. But you can use a similar argument as before and it still works. Okay, so we still have that is true. Okay, so let's look at the smallest element of D, 0. And then let's say that's A. And then let's look at the set X for every X that's phi of Q less than A. This is an infinite computable set. You can just sort of test each value. So there's two cases. This can either have an infinite descending sequence in phi of Q, and let's say that is D1. So if I take the union of D0 and D1, right, D0 was a descending sequence. D1 is now a descending sequence. That should be a solution on that side, on that ADS side. But this is a contradiction because on the X and the X prime, this is still going to agree because we chose U to be large enough. It's still going to agree with the part that we made sure wouldn't extend to a solution, right? So we made sure that x and x prime can't extend to a solution, and now we're saying that it does. So that doesn't work. So if it doesn't have an infinite descending sequence, then it has no infinite descending sequence. So again, similar argument to before, there has to be a computable ascending sequence A in this linear order, right? But then that means that psi of q join A is a computable solution, but we made sure that what we chose was something that had, well, it was something finite first, and then on top of that, I had something with no computable solutions, but these are both computable. We take computable function on that, it should still be computable. There's no computable solutions, so that also does not work. And then because we came to a contradiction in both of these cases, that means that indeed this couldn't be a Weierach reduction. So it was computable. These two problems were computably, QADS. I guess the one that we want to look at is QADAC. We showed that that's computably reducible to ADAC. And then hopefully this can be sort of modified to show that they're not Weierach reducible. Okay, so another theorem would be ADAC is not computably reducible to CAC, right? And then from here we can sort of get our end goal. So in order to show this, anytime you have a non-reducibility for computable reduction, it's a little harder because, again, we don't have this uniformity to look at. We can't just choose two functionals, right? It could be a bunch of different functionals that we get to use, right? So it's a little harder. And so one thing that's nice to use is sort of finding a property that should be preserved under computable reducibility that the one on the right has, and then the one on the left doesn't. So the one that was used for this one was this, uses this definition introduced by Ludovic Bataille in his thesis, and it says that a problem P admits preservation of P among K hypermunities if for each collection of K hypermune sets and each computable P instance X, there is a P solution Y to X such that P of the K hypermune sets are Y hypermune. So one way to remember, or there's a couple different definitions of hypermune. One way to think of a hypermune set is that its principal function is not dominated by any computable functions. And then, of course, you can relativize that. You could say Y computable functions, right? So that's what it means to be like Y hypermune, right? So we're taking, we're starting off with K hypermune sets, and then showing that anytime I have a computable solution, or a computable instance, and I find a solution to that, then at least P of those are still going to be hypermune relative to that solution, right? Maybe not all of them, but at least a certain number, right? So P in this instance. Okay, so the way I'm separating this is CAC preserves 2 among 3 hyperimmunities. What you do is you fix 3 hyperimune sets, and then what I did was I used a forcing where I sort of, it's kind of like a Matthias forcing, but with more restrictions, and I sort of have these 2 sets that are going to be an anti-chain and a chain. And then in the end, right, I made sure that they are, that each of the hyperimune sets are hyperimune relative to one of those. And then if I have 3 hyperimune sets, each one I have to pick between which one it might be hyperimune relative to. By the pigeonhole principle, like one of those has 2, right? So that's why it would preserve 2 among 3. It turns out with ADAC, it's not the case. We can find an instance of ADAC, and we can find 3 hyperimune sets such that two out of the three are not hypermune relative to any solution to the instance. Okay, so first I proved that there's a weakly stable partial ordering. And so what weakly stable means is that every element is either large, which we've talked about, and then or small, or isolated, which means that it's incomparable to cofinitely many elements. So it has to go in one of those categories. So it's sort of, so what we do is we have that there is this computable weakly stable partial ordering, and that each of the pairwise union of the set of small elements, the set of large elements, and the set of isolated elements are hypermune. So those are going to be our three hypermune sets that we get to choose. The pairwise unions of these sets are also going to be hypermune. And then an ADAC solution to this partial order would be an antichain, ascending sequence, or descending sequence. And so an antichain would be a subset of the pairwise unions containing the set of isolated points. So right, there was two of those. And then, ascending set of small elements, descending were the unions that contain the set of large elements. So in any of these cases, there will be 2 out of 3 sets that are not hypermune relative to the solution because they're subsets. Okay, so then that would give us this non-reducibility. If we suppose to the contrary, then we can use what we found for the ADAC proof. We can use those sets and also that partial order. Then any CAC solution is going to, let's say it has a solution, or any CAC instance is going to have some solution C. And then together with the original partial order, we can compute a solution A. And then 2 of the hypermune sets are C hypermune. And so no C computable function dominates either of the principal functions of these sets. But we have that A is computable from C, so any A computable function also can't dominate these principal functions. But that would be a contradiction of how we chose them. Okay, so sort of finally wrapping it up, I had a little extra stuff in there that is not necessarily necessary for this proof, right? The long proof that I showed. But this is sort of the main idea. And now we can show this, right? We have that ADAC is computably reducible to QADAC. So we have to have, we must have that this is the case, that this non-reducibility is the case, because otherwise, since computable reducibility is transitive, we would get that ADAC is computably reducible to CAC. That was the one I just showed is not true. And then, of course, we have the strong Weierach equivalence, and so it's true. It's also true that WJSCL is not computably reducible to CAC. So even though they are equivalent over RCA naught, they're not computably equivalent to each other. So here are some of the references I use. So that's paper I co-authored and some of the other ones. The original one, the Ginsburg and Sands one, is right there. But other than that, that's it.